Welcome, 7th grade scientists, to this explainer. Okay, right now, just think about what you're doing this very second. You're probably sitting in a chair, maybe holding a device, kind of shifting your weight around. Well, without even realizing it, you are locked in this constant invisible battle with the physical world around you. We experience these invisible mechanics every single second of our lives. Today, we're bringing those invisible hands into the light by diving into Unit 1, Lesson 2, Balanced and Unbalanced Forces. Get ready for a really fun, high-energy look at the mechanics of motion that shape literally everything happening around us. Let's get into it. Okay, let's dive into this roadmap. First up, we'll look at the forces around us. Then, we'll be modeling forces in action, and finally, applying forces to systems. So here's the big essential question for this whole unit. How can forces explain changes in motion? I mean, have you ever wondered about those invisible hands that cause everyday objects to suddenly dart across a room or just come to a screeching halt? Like, why does a skateboard fly forward when you push off, but eventually roll to a stop? That's exactly the mystery we're going to solve today.
All right, moving into Section 1, the forces around us. Before we can engineer any massive space solutions, we've got to lock down the basics.
So what is a force anyway? At its core, a force is simply a push or a pull acting on an object that can cause a change in motion. This is the fundamental building block for everything we're doing today. Think about pulling open those incredibly heavy double doors at the front of your school. You're exerting a massive pull, right? Or, hey, think about what's happening right now. Gravity is constantly, relentlessly pulling you down into your seat. Actually, scratch that. If your chair wasn't pushing back up against you, you'd fall right through the floor. Crazy, right? So whether you're kicking a soccer ball, dragging a heavy backpack, or just sitting perfectly still, you are dealing with forces.
Now, what's really interesting about this slide is the difference between balanced and unbalanced forces. Picture a massive game of tug-of-war between two perfectly matched teams. They're sweating, straining, pulling with all their might, but the rope? It doesn't move a single inch. Those forces cancel each other out perfectly. The sum of those forces is exactly zero, which means we have balanced forces. And because they're balanced, the object's motion does not change. But imagine a giant suddenly joins one side. Boom! One side is pulling way harder. The sum is no longer zero. We now have unbalanced forces, and that means motion changes. The losing team goes flying forward. Unbalanced forces are literally the reason objects speed up, slow down, or completely change direction. Let's move to Section 2, Modeling Forces in Action, and see how this science operates in the real world. Let's look at this data. Imagine you and a sibling are fiercely fighting over a heavy box of old video games. You're both pushing on opposite sides of the box, trying to slide it your way. If you both push with the exact same strength, matching each other pound for pound, those are equal opposing forces. The result? Zero motion change. The box stays perfectly still in the middle of the room. But let's say you push much harder than your sibling. Now the forces are unequal. One side overpowers the other, you've got unbalanced forces in play, and that heavy box slides right across the floor. The difference in applied force completely dictates the resulting motion.
So how do we predict exactly what's going to happen to an object? It's kind of like a scientific superpower that lets you see the future. Here is the step-by-step. Step 1. Identify all the forces acting on the object. Gravity pulling down, friction dragging against the floor, a physical push. You have to count every single one. Step 2. Determine their directions. Are they working together as a team or fighting against each other? And Step 3. Calculate the sum to predict the change in motion. Remember, an object's motion is always determined by the total cumulative sum of all the forces acting on it.
And this brilliantly illustrates a core scientific principle. The greater the mass of the object, the greater the force needed to achieve the same change in motion. Mass matters a lot. Imagine you're at the grocery store. Pushing a totally empty shopping cart down the aisle? A breeze, almost zero effort. Now imagine filling that exact same cart to the brim with heavy bowling balls. Trying to get that cart moving or stopping it once it gets going requires a massive amount of effort. The more mass something has, the more it stubbornly resists any changes to its motion. You need a way bigger push or pull to get it to do what you want.
Which brings us to our final stop. Section 3, Applying Forces to Systems. Let's take all these concepts and apply them to a real-world scenario. So the crucial point here is Newton's third law. It states that for any pair of interacting objects, forces are equal in strength and opposite in direction. This is the ultimate key to unlocking how collisions work in our universe. When object A hits object B hits back with the exact same amount of force, but in the opposite direction.
Think about the last time you accidentally stubbed your toe on a door frame. You hit the wood with a lot of force, but guess what? According to Newton's third law, the door frame hit your toe back with the exact same amount of force. The door frame didn't swing a foot at you, but the physical interaction meant it returned that exact same force in the opposite direction. That is exactly why it hurts so much.
All right, let's look at your final transfer task. You are stepping up as the lead engineer here to design a collision solution. You'll need to apply Newton's third law to interacting objects. And we aren't just talking about rolling marbles. You're going to analyze a collision between two cars, and even more epic, a high-speed collision between a meteor and a space vehicle. You'll have to predict drastic motion changes based entirely on mass and force. The success of the mission rests completely on your understanding of these forces.
And that leads us to our final mission-critical question to wrap up this explainer. Based on the sum of the forces, how will you design a solution to protect a space vehicle from a meteor collision? Think about the massive force involved in a deep space impact. Think about Newton's equal and opposite reactions and how you can manipulate mass and applied forces to keep that spacecraft completely safe. You've got the tools, you know the physical science. Now it's time to solve the problem. Have fun with your design solutions.